Hey everybody, today we'll do another quick video. It's going to be on power systems. So today we will do simple problems. It's going to be like more like an application of real, real life situation. Which basically that's what we do in real life, right? So the first one is it says it says the first one it says a three phase a three phase motor. Three phase a three phase motor can be regulated, can be regulated as a balanced wide load as a balance balance wide the, the three phase motor draws 5 kilowatts. Okay. Uh three actually three phase the three phase motor motor a three phase motor draws um the three phase motor draws 5.6 kilowatts of 9 kilowatt when the line voltage when the line voltage is inline current line voltage and line current volts and line current it is 8 okay so 18.2 amps, right? um Determine the power factor of the model, right? So question is determine the power factor factor of the the so we're looking for the power factor. This is what we're looking for, right? We're looking for this. Right? All this stuff over here is important, right? But we should focus in just this, but it's important to read, right? What it's saying. So it's saying that the motor draws 5.6, oops, 5.6, 5.6 kilowatts, right? It's important for us to know that. It is also important to say to this is important. This is important. Yeah. Dysregulated, I don't care about it. I don't care if they apply in BFTs or they apply in anything to regulate that. What I care is about three-phase, about the imbalance, about this, right? And about the power, the real power, and about this, right? Remember that to find the power factor, we can do a couple different things, right? In this case, we don't know anything else. We just know the real power, right? But we know that S, which is the apparent power, right? S is equal to S is equal to the S is equal to the square root of the voltage multiplied by the line current, right? So with that being said, so we know that the square root of 3, which is a three-phase system, right? Because that is important to understand that it's a three-phase system, is, all right, so B line, square root 3 times B line, BL times IL, right? So S, which is the apparent power, right, is going to be that number, right? So S, in this case, the line, the voltage that was given to us, right? I think it was given to us the line voltage, and I did not write it down. Okay, there's another important piece of information. The line voltage. Okay, so line voltage. Read 240 volt, right? Airline current is 18 amps, right? So that's very important. Right? So now, I don't know if the China virus coming up again, but whatever that is, CPP virus. Um, and again, this is the Conservative Engineering Academy, so I like Chinese food, right? But I'm saying China virus. I am not saying Chinese virus, right? I am not trying to be politically correct right here, right? So I'm just saying, right? I'm just saying China virus. So, okay. So what we did right here is calculating, right? So we calculating this. Um, so it's going to be the square root of 3, right? Times 240 volt times 18.2 amps, right? So when we do that math, we do the math, right? So we just do that. And this is nothing but, okay, so this trick here, right? So 1.732, right? Times 240 times 18.2, right? So that is, actually, it's 240 or 220. Let's see, what is the value of that? And make sure that, actually, it's 220. 220, right? Okay, 220 volts, right? So times 220 times 18. So that is equal to 6,924.2 volt amperes, right? Now, because we got a amp power, right? We got a amp power out of that, right? So now that I have that, right? So I can say that the parent power is equal to, because S is equal to, because, because, so we can actually say a couple different things over here, right? So we can say that P is equal to S, right? Which is the apparent power times cosine of the angle theta, right? What we can do is right here, we can say that, and of course, as you know that this is the power factor, right? So now what I can say is cosine of theta is equal to divided by S on both sides, right? Divided by S on both sides. And I can say that cosine of theta is equal to B over S, isn't it? Now, what I can do is simply just cosine of theta, which is the power factor, right? Is going to be in this case, right? Making this 3 decimals to the right because it's a kilowatt. I'd say that that is right. So it's going to be 5600 over that number, right? 6934.2. Okay. So when I do that, take that and I say 56600 divided by second answer, and that give me a power factor actually of 80%. That give me 80.8 power factor, right? 75. Or you can say that if I move this to the right, you can say that this is close to 81% power factor. Okay, so that is the power factor, right? Okay, so you can see that basically you can also say that that's a zero point 0.8 power factor is also, it depends, you want to round it up, right? Now, one round it up, if not, you get 80%, which is, pretty close. Right? So that's one question. Now let me do another quick question real quick. Okay, so that is how to find the power factor, right? Now, so that motor is really a natural. From this you can find it, the efficiency of the motor. Also, you can find it from there, which probably, I don't know if I will do problems like that, but you can play with the numbers and the formula, and you will understand that this is a beautiful thing. How to, after you understand this, it's the efficiency depends on the power factor, right? And the efficiency of the motor also depends on the power factor, and also the power factor depends on the efficiency of the motor. They kind of, right? Now, what I can do here is another problem real quick, which it says the following. It said calculate the line current required. So it says calculate the line current require, right? Require, require, require. Click the line current require. So for a for a 30 kilowatt, 30 kilowatt, um, 30 kilowatt, three phase motor. Right. So let me just do it backwards. Three phase motor, right? Three phase motor, all right? Having a power factor of having a power factor of 0.85 lagging, lagging. Okay, so okay, lagging, right? So lagging. Yeah. So this having a power factor of lagging, if it's connected, if it is connected to a balanced source with 440 volts, right? If, if it is connecting to um, a balanced source, is this connected? If it's connected to a balanced source, right? To a balance source of 440 volt, right? Line to line, right? And I believe that just says line voltage, right? Line, line voltage. Yeah. Okay, so now as you can see, the power factor was given, right? Power factor was given, right? So as you can see that the power factor is given, and we need to pay attention to some words. We pay attention to this guy, of course, and also this guy. This is very important, right? It's less than the power factor. Important to pay attention to this line to line. It's line voltage, right? It's a line voltage. It is important to pay attention to this and to this. If anything else, pretty much like, this is important. All right. So now it is important to the what is being asked, right? We are being asked to calculate the current required for this system. Now, so as you know that B is equal to X as right cosine of data, we can actually see if we can find some of those stuff, right? So first of all, let's say that we have the the power factor, but we have it because it's lagging, which mean that this is negative. It's not telling you that it's negative, it's just telling you that it's lagging, but the power factor indeed is negative. So what we can do is, you can say that power factor equal to cosine of data, right? Now what you can do is take the inverse. Data is equal to cosine of the inverse of the power factor, right? Power factor inverse, right? Now notice that this guy is negative because it's lagging. So data is going to be equal to cosine, right? It's going to be cosine of the negative 0.85, right? Now, doing that, we get we get the inverse, the inverse root of 0.85 negative is equal to, now remember I find data, so that is equal to 140, okay, 148.21 degrees. Right. Look at that. So look at that. Where is this located? So that mean that I am right somewhere, maybe somewhere over there, maybe, right? So the angle go like this, maybe a little up, maybe. Yeah. So this is the angle what I'm looking for, right? So if I draw a perpendicular line, I am here. So this is 148, 148.1 degrees, right? Now this is 180, right? This is 180. So that means that I need to subtract this guy, right? I need to subtract 148 from 180. And then when I do that, I get 180 minus, I can answer, and I get 31 point, I get 180 minus 148.21 is equal to 21.9. So 31.9 degrees, right? Now, 21.9 degrees. Right? Now, very important. Now, what do I need to do? Okay. So what I need now is that to find this guy, right? I need to divide it by that angle, right? So knowing that this guy was given to me, so to find S, right? I can say that S is equal to P over cosine of the angle. Now, when I do that, so I get 30,000, right? Divided by, divided by, divided by that. So I get a tenth, right? So what did I do right here? Just divide it, right? Divide this guy, right? By cosine. I don't want to get somebody lost over here, so I want to just cosine the data on both sides, right? So this cancel out, and I get that x is equal to p over that, right? Now it's very important, right? Very, very important step to do. Now, when I do this, right? So x is equal to 30,000, right? 30,000 equal over cosine, right? Because it's in kilowatt, so I just multiply by 1,000. So cosine of data, which, okay, so cosine of the angle data, right? Which in this case is 31.9 degrees. And this is equal to what? This is equal to 35,200, 35,290, 94. Right? 35,294 VA, volt amperes. Okay, now look at this. Now I have two pieces to work with. Now, now, if this that means S is equal to that, right? So, and remember that S is equal now. So now I can say that S, right? Because I found F. S is equal to the square root of 3 V line times I line, right? So I have an S, right? So S is this guy. So what I can do is replace S, and I can say that 35,000, 35,200, 294 VA, right, is equal to the square root of 3, which is 1.7, you can say 1.732, 1.732, right, square root of 3, times what? Time V line. V line in this case is what? V line is, yes, V line, right, is 440 volt, right? And times I, right? That's why I am looking for I line, right? Doing all this stuff, I get that. So 1.732.732 times force. So that is equal to, so this is equal to 94, right? Is equal to 762, right? So 35 to 94 divided by second answer is equal to, right? I line, that's what I'm looking for, right? So divided by 7.62 on both sides, right? 7.62, right? Remember that this is the product of this, right? So, all right. So when I do that, so I know I get that I line, right? In this case, it's going to be equal to 46, 46, 46.3, 46.3 amps. Okay. So you can see that that's how yes. Isn't that beautiful? See how you can apply the basic mathematics that you learned this in high school. If you pay attention, see how you're playing with the degrees, with the angles, right? You got a 180, you got that guy minus this guy minus that guy, giving you that guy right there, right? And then you're playing with your little formulas, and you found out that the I is equal to 46.3 amps. Beautiful. It's beautiful. So, okay, so that's it for tonight. If you enjoyed this video, give me a like. And remember that over here in the Conservative Engineering Academy, we learn a little something every day because Jesus is good, right? And that's it. I hope you have a wonderful day, a wonderful night. If you are overseas, you might be having a wonderful day, right? And if you have here, if you are over here in the United States, you might be having a wonderful night, wonderful night. So whatever you are, just bless you.